Okay, so in the previous lesson we talked about logarithms and were introduced to the concept. So hopefully you're understanding those after working on your assignment. But today we're going to be looking at two specific areas dealing with what we call logarithmic scales. This would be where we would apply logarithms. One of which is relating to sound intensity, which is measured in decibels. And a formula that relates to sound intensity and to its relative intensity, D, in decibels, is given by this formula. And I want to make sure you write this down. We're going to use this a little later on. You'll use this in your assignment today as well. Also, you want to write this other equation down. Now, this formula represents an increase of n decibels multiplies the sound intensity by 10 to the n divided by 10 power. So here's where we're going to use that particular problem. So let's look at this example. It says, well, first off, before we do that, this gives some different sound intensities measured in watts per square meter. And you're familiar with seeing things measured in decibels. For example, maybe you'll hear that a lawnmower is 80 decibels. When you go to the school dance, that's approximately 100 decibels. But that sound intensity in watts per square meter would be equivalent to 10 to the negative second power. Or an electric drill or a lawnmower. Electric drill would be at 90 decibels or 10 to the negative third power as watts per square meter. A whisper at 5 feet is 20 decibels. So this gives us a scale as far as measuring how loud or how intense sound is. So due to a law in France, manufacturers had to limit the sound intensity of their MP3 players to 100 decibels. How many times as intense is a particular MP3 player's maximum 115 decibel intensity than the limited intensity imposed in France? So here we're trying to figure out 100 decibels as opposed to 115 decibels. How many more times intense is 115 decibels than 100 decibels? Because it's only a 15 decibel difference, which may not seem like much. Well, we want to figure out how many more times intense that sound would be. So this formula here represents an increase of a certain decibels. So I'm going to use 10. My increase of 15 decibels is going to be my value for n. So I would do this in my calculator, take 10 to the 15 over 10, or 10 to the 1.5 power. When you do that on your calculator, you get 32 as your answer. So what that means is our answer of 32 is that 115 versus 100 decibels is really 32 times more intense. So to figure that out, you take the difference in the decibel value, and divide that by 10. So in this case, my difference here is 15 decibels. Divide that by 10 gave us 1.5. So it would be 10 to the 1.5 power gives me 32. So let's compare 125 decibels to 105 decibels. So again, my difference here would be 20. This we could do without a calculator, because 20 divided by 10 in our exponent there gives us 2, and 10 squared is 100. So here, a difference of 20 decibels means that it's 100 times more intense. Would be your answer. Let's look at this one. It says, grunting while hitting the ball has become a controversial issue in professional tennis. And you'll have a problem dealing with this in your assignment today. Some people are concerned that such loud sounds are unfair distractions to the opposing player. Serena Williams' grunts have been measured at a sound intensity of 6.31 times 10. I don't know what happened here. Let's change this. It's 6.31 times 10 to the negative fourth power, and this is measured in watts per square meter. That's what that's supposed to say. We're going to find the relative intensity of the sound in decibels. So to do this, what we're going to do is we're going to use that equation that we talked about at the beginning. which is this, d equals 10 times a log of n divided by 10 to the negative 12th power. So what this is going to do is this is going to convert this to decibels. So I'm going to replace n in my equation here with the 6.31 times 10 to the negative 4th. So essentially it's going to be d equals 10 times a logarithm of 6.31 times 10 to the negative 4th. For the purpose of the problem, I don't need the units right now. Divided by 10 to the negative 12th power. So I'm going to do this on my calculator. So when you type that in, you can do this in parts. Take the logarithm of this whole quantity. Now you want to make sure that you do that in parentheses. So why don't you see how I type that in here. Okay, so you should have your calculator on. So we're going to type this in. Now, the nice thing about the CAS calculator is you can do all this all in one step. So I'm going to type in 10. And then the log button is above that 10 to the x power. This is a common logarithm, so again, you don't need to put anything down as a base. If you want to, you can. But then in parentheses here, I'm going to type in, actually I'm going to do this. If you hit the control divide button, it gives that fraction bar, so we can make sure that we do this correctly. Then it's going to be 6.31 times 10 to the negative 4th power is my exponent. Move down to the denominator. It's going to be divided by 10 to the negative 12th power. Hit enter and you get 88 as your answer. So 88 decibels is what this would be equivalent to. Now a note on this, if you don't have a CAS calculator, you want to make sure that you do this correctly. Make sure that you have parentheses around this quantity. The fact that you're multiplying 6.3 times 10 to the negative 4th divided by 10 to the negative 12th, you shouldn't have to worry about your calculator making any mistakes there. But it's very important. The nice thing about the CAS is after you hit enter, it'll always show you what it entered in, so you can double check and make sure that you did it correct. So again, we get 88 decibels as your answer. Okay, why don't you work on this next one on your own. Find the relative intensity in decibels. In other words, we're going to use the same formula of a muted conversation, which a sound intensity is 3.16 times 10 to the negative 8. So we're going to see what the decibels of this muted conversation would be. So go ahead, work this out again using that same formula. So pause the video and hit play when you're ready to check your answer. Okay, this is what you should have typed in on your calculator. 10 times a logarithm of the sound intensity, which is 3.16 times 10 to the negative 8. All that divided by 10 to the negative 12. So when you type that in on your calculator, you should have gotten an answer of 45 decibels. Okay, let's look at another situation. Here they give us the decibels. The maximum sound intensity of Melody's MP3 player is 115 decibels. What is a maximum sound intensity in watts per square meter? So this time we're going to go the other way around. This time they're giving us the value in decibels, and we need to figure out what it would be in watts per square meter. So we're going to use that same equation. So again, it was, just copy it here. So you want to make sure you get this in your notes, at least that formula. So we're going to put 115 in for the decibels. So 115 equals 10 times a log of n divided by 10 to the negative 12th. Now I want to get the logarithm by itself, so I'm going to divide both sides by 10. So when you do that, you get 11.5 equals the log of n divided by 10 to the negative 12th power. Now here's a problem. I'm stuck. I don't know what to do. I have this variable here in parentheses, and the logarithm of a variable. How do I do that? We haven't learned anything about doing something like this. Well, remember in the previous section I said if you're ever stuck, if you don't know what to do, try rewriting it in exponential form and see if that helps. That's what you're going to have to do in this problem. Remember, you're dealing with a common logarithm, so the base is 10. So we're going to take and rewrite this in exponential form. So it's going to be 10. Remember, when we have a logarithm, it's equal to the exponent, which is 11.5. And now the log is gone. So it's going to be n divided by 10 to the negative 12th power. So to solve this, I'm going to multiply both sides by 10 to the negative 12th power. So n is going to equal 10 to 11.5 power times 10 to the negative 12th power. Or remember, when you multiply and the bases are the same, we add the exponents. So 11.5 plus a negative 12 would be a negative 0.5. And when you do that on your calculators, you get an answer of approximately 0.316. This would be in watts per square meter. A little note about rewriting something in logarithm form that a teacher once told me that might help you. If you have something written like this, and we want to put it in exponential form, basically, remember this is your base, so if I slide this over, now when you slide that over to the other side, you drop the log, so it would be x equals 10 to the 7th power. A little note about how to rewrite something from logarithm form to exponential form. Again, what I just did there, you slide the base over. So when you slide the base over, the 7 is going to now become your exponent for that base 10. But when you slide it over, you can drop the logarithm. So it would be x equals 10 to the 7th power. Maybe that'll help with this next one. Why don't you try this next one on your own? A very loud rock band plays at a relative intensity of 125 decibels. What is the sound intensity in watts per square meter? So again, you reuse that same formula and solve it for n. So pause the video and hit play when you're ready to check your answer. Okay, so let's see what you did. You should have set it up like this. We have the 10 times a log of n divided by 10 to the negative 12th power equals, in this case, 125 decibels. So now I'm going to divide both sides by 10. Which gives you 12.5. Again, I'm stuck here, so I'm going to rewrite this and put this in exponential form. So it'll be 10, our base 10. Our exponent's going to be 12.5 equals n divided by 10 to the negative 12th. You can cross multiply here or multiply both sides by 10 to the negative 12 to get n by itself. So n would equal 10 to the 12.5 times 10 to the negative 12. When you add the exponents, you end up getting 10 to the 0.5 power, which equals 3.16 approximately watts per square meter. And there's your answer. Now there's one other situation. So we've been talking a lot about decibels. The other one that we're going to talk about is dealing with earthquakes. You hear about earthquakes being talked about a lot on the news when they occur, and they're always measured according to the Richter scale. The Richter scale follows as a logarithmic scale. Now here, this Richter scale, this table here just talks about some different effects that will happen. Like let's say if you have a Richter magnitude of 3, means that it's going to be felt but rarely causes any damage, all the way up to a magnitude 8, which means that few buildings are going to survive and there's going to be landslides and all sorts of problems. So like the decibel scale, the Richter scale is a logarithmic scale. A value of x on the Richter scale corresponds to a measured force or amplitude of k times 10 to the x power, where the constant k depends on the units being used to measure the quake. And just a little hint on that, K really is not going to come into to be a factor at all for these problems. You'll see what I mean when we look at this example. It says just before a 1989 World Series game in San Francisco, California, there was an earthquake that registered 6.9 on the Richter scale. I remember watching that game and watching that earthquake happen. The tsunami that hit 12 Indian Ocean nations in December of 2004, maybe you were alive when that happened or remember that happening, was triggered by an earthquake that measured 9.3 on the Richter scale. The force of the 2004 earthquake was how many times the force of the 1989 earthquake? So 6.9 and 9.3 really don't seem like it's that big of a difference. But let's see how when we use the fact that these are based on a logarithmic scale, we want to figure out how many times, in reality, how many times larger, how many times more intense the 2004 earthquake was than the 1989 World Series earthquake. So here's how we figure that out. We're going to divide these. We're trying to figure out how many times more intense the more recent one is, which was 10.93, than the 1989 earthquake, which was 10 to the 6.9 power. Now really it's k times each of these, but if I take k times 10 to the 9.3 divided by k times 10.69, the value of k is going to be the same for both of those, so they'd cancel out. So in other words, when we're finding the measure of these, you really don't need to worry about that k. So it's going to be, again, 10 to the 9.3 divided by 10 to the 6.9. Do that on your calculator. Or we can even simplify this because the bases are the same, so we can subtract the exponents. So these are equivalent to 10 to the 2.4 power. But when you do that on your calculator, you get 251.2. So that means the 2004 earthquake, U, was 251.2 times more intense than the 1989 quake. So when you see it in terms like that, seeing those numbers make a bigger difference, because 6.9 or about 7 versus about a 9 on the Richter scale is about 250 times more intense. Why don't you guys try this one on your own. On May 12th of 2008, China was hit by an earthquake that registered 7.9 on the Richter scale. How many times greater was the force of the 2004 earthquake, from the one that we just talked about, than the 2008 earthquake? So go ahead and we can go ahead and set this one up together. So it'll be 10 to the 9.3, that was the 2004 earthquake. We're trying to figure out how many more times intense than the 7.9 earthquake. So when you divide those, why don't you guys go ahead and try that on your own. It'll just take a second. And you can pause the video if you'd like and hit play when you're ready to check. See how you did. And when you divide these, if you got your answer now, it should have been 25.1 times larger, or 21 times more intense. So hopefully after watching this video you can see how logarithmic scales apply to some real life scenarios. When we're dealing with earthquakes, it's real easy. You just take 10 to whatever the Richter scale is as your exponent and divide them to compare these to figure out how many times more intense one is than the other. When you're dealing with decibel levels, remember we had this formula to figure out if we need to convert from watts per square meter to decibels, or we could use this same formula to convert from decibels to watts per square meter, as we did in examples 2 and 3. And if you want to figure out how many times more intense it is, you would take your decibel levels, the difference in the decibel levels, remember that's how we got 20 here, and divide that by 10. So take that to the 10th, or apply that exponent to our base 10, and that gave you how many times more intense one decibel level was than the other. So hopefully you understand that, and good luck on your assignment.